And so again, 9.4 models of population growth. We've already spent a good chunk of time talking about this. This is sort of the ideal population growth. This is just kind of your simple exponential equation. This is the more basic example here. And of course you might have like some occasional modifications to this. The book kind of gives accounting for like immigration or harvesting by if you have some rate, you just subtract it from this guy, but in the end it still remains the same. You might just have some extra constant piece that's going to be added on that's going to be dependent on whatever that subtraction value is. But that's not going to be as big a deal for our discussion. What is going to be a big deal for our discussion today is going to be working with the logistic model is what it's called. Okay, which if you remember, if I have my population is going to have a certain point where it's going to kind of slope off because I may not have the resources for all of the people. Like I may expend my resources, and so then my population, instead of increasing, is going to start decreasing, right? And so to factor in for that, right, we still had our general growth direction, which we had the K times P, but we also had to factor in the carrying capacity piece, which looks like 1 minus P over M, where M, right, so K is the relative growth rate, same as over there. And M is the carrying capacity. Okay, so up until M, my population should be increasing, but once it passes M, it's going to start decreasing, right? Now, what's going to be in real life situations a lot is most systems are going to look a lot more like this one than they are going to be like this one, right? Because in reality, we don't always have like a perfect growth situation, right? Like obviously, if every which we'll get into predator stuff in 9.6, but if every animal living thing on the earth grew at this ideal rate, it would be crazy. So we don't have that. We want to look at models like these, right? But who wants to deal with the hassle of working this out each time, right? We can just take the general form and solve for it, right? So that's what we're going to do. We are going to solve this differential equation for B, for what it's supposed to be. First, maybe it's good to kind of get an idea of what it might look like in general. And I'm just going to draw mine more in an abstract form, but the book does give a particular example if you want. But just like with other differential equations, I can create a direction field for this to see what my solutions are going to look like. And right, this system is going to have some equilibrium points, right? So what are the two equilibrium solutions of this equation going to be? Right, what numbers do I plug in to make this thing 0? 0 or n. If it's 0 or if it's the carrying capacity. Okay, so all along this x-axis, I should imagine I kind of have flat direction lines, and at the m value, I'm going to imagine that I also should have some sort of flat lines in this case, right? I have my flat direction lines. Okay, from here, right? If you're to keep testing numbers, what you're going to get is, if we start lower, your slopes aren't going to be very big, but as we kind of move up, they're going to start looking a bit bigger, right? And this may not be the perfect drawing, but again, it's just kind of showing for illustration, but what's going to end up happening with this curve, right, is my population is just going to grow as normal first. It's going to say, okay, right, because we can kind of see where the curve is going. It says, okay, I'm going to start my population, and hey, oh, we're going good, we're getting up there, but at some point, things are going to start changing, right? Like things are going to start leveling out a bit more as I get closer to this carrying capacities because I'm slowly running out, right? And I'm slowing down, right? And then I kind of, in a way, kind of hit that carrying capacity, right? And for most populations, it might slow down a little bit, but it's going to generally just kind of more gravitate towards where that's going, as you can see from all my slope lines and stuff. But this is the general curve of my graph in this case. This is what we're going for, right? Same thing would happen on top, except in sort of a different form where it might start big, but then it sort of slopes down. But this is sort of the graph we're looking at, where it starts to build, and then it stops, it kind of slows down, it gets to a certain point. So whenever you're thinking of what the graph of that thing looks like, this image right here should be what's in your mind, right? It builds up, and then it slows down, kind of gets to the stopping point, right? And luckily, we can find the exact function that does this, right? That's going to, instead of just using our slope field to draw the solutions, we're going to find this exact solution, okay? So let's start off. Let's see, I'll use, okay, so again, our equation is dp over dt ap times 1 minus p over m. Okay. Now, if I'm solving this differential equation, right, my first idea would be to try to make it as simple as possible. And since I have this fraction here, I kind of want to get rid of it. Okay. So what I'm going to do is I'm going to take both sides of this thing, and I'm going to multiply it by m. Okay. On the left side, I'm going to get m times dp over dt equals ap times m minus p, m minus p, okay, so I simplify this. Okay, now notice this is in 9.4, right before we do 9.5. So what sort of differential equation do you think this one is? What is it? Right, it's not going to be a linear, right? Again, this came before we learned about linear differential equations, right? This is a 9.4, and that was 9.5. It's a separable one, okay? Notice there's no t in here, so it's a really easy separable equation because there's no t to worry about. So I can just take all the p stuff and move it to one side, and take the dt and move it to the other. So that's exactly what I'm going to do. I'm going to take this kp m minus p, bring it down, and then take the dt up. Maybe I'll leave that k there, but I'll take the p stuff and move it over at least. So I'm going to get m dp over p times m minus p equals k dt. Okay, fantastic. What do I do from here? We would integrate now. Okay. Who can tell me how I would integrate this left side? Right, so I have dp and I have p times m minus p. What rule would be the most advantageous for us to integrate this left side? What technique? Not a u sub really, because there's not really a good pick. I mean, because if you say u is m minus p, then I would just shift it here. It would be 1, so not u sub. So we can't simplify it really. There's no u sub. Maybe integration by parts. I think there's a better one. Not trig sub. Definitely not trig integration. Or fraction, right? This is a rational function, is it not? I have just a numerator over denominator, and they're all polynomials. So we can do partial fractions on this. So I'm gonna have, so this is gonna turn into A over P plus B over M minus P on this side in some way. Okay. Now we need to figure out what A and B are supposed to be. So let's do that real fast. Maybe I'll do that in a different color. Separate our work. I'll use the purple here. So, right. So we want A over P plus B over M minus P. We want that to be equal to M over P times M minus P. Okay. So what do I do to both? What should I do to both sides? Good. Okay. So that's going to cancel out the P here, give me A times M minus P. And then we're going to get B times P. It's just going to be M on the slope side. Okay, good. Now, I showed a couple ways to do these problems, right? You can either just set, like kind of distribute and put things together, or we can just plug in numbers, right? So maybe I'll just plug in since it's a pretty simple partial fractions in this case. So I have M minus P here and I have P here, right? So any guesses? What might be a good P to plug in? 0 or M, right? So we might do both of those, right? Because that's going to cancel out each of those terms respectively. Okay. So if I let P be 0, I'm going to get A times M plus B times 0 equals M. So basically AM equals M. So what is that? A. Fantastic. Okay. If I do P equals M, I'm going to get A times 0 plus BM equals M. So what's B going to be? B is also 1. Okay, so this is actually a pretty easy situation. They both just end up being 1, right? Which makes sense. If they're both 1, then I get M minus P plus P, which just gives me M. Okay, good. So there, continue our green here. So this needs to be 1 over P plus 1 over minus P d. Okay. Can I integrate each of those? Yes, we can. What's the integral of 1 over P? Yeah, which honestly in this case, since P should be positive anyway, it doesn't matter. Maybe we'll keep it just for the sake of the M minus P though, just in case that's negative. Okay, now what is the integral of 1 over M minus P? Right, so it's just P with a constant, so that should just be able to come up in M minus P. You can do it yourself if you want to do that, which is fine. We're going to get this, but with one addition, it needs to be negative. Because since it's minus P, I need to counteract that minus. So, okay. So I get LP minus out of M minus P, and we want this to be equal to the right side. What's the integral of the right side? KB, or K. And then we have a plus a C term still. Okay, good. So we're at this point. It would still be an advantage for us to solve for P, not just leave this as it is if we can, right? So if I want to try to solve this thing for P, what might be my next step? What is it? Okay. Yeah, so we will take e to everything. I would combine the logs first. It's not wrong to take e because it will work out the same way, but it might be easier to think about if I take both the logs and combine them together, right? because if I have, and I'll write this for everyone, the natural log of A minus the natural log of B, this is the same thing as the natural log of A divided by B. Okay, so in my case, I get the natural log of P over M minus P equals C. So here, I'm going to raise both sides to the E, which will cancel out the natural log, bring that down. So we're going to get P E over M minus P, and it's going to be equal to C. This plus C is just going to kind of come down. I need to see if they. Okay. So we're going to get, I'll just write it as E to the C right now. E to the E. Okay, so we're left with this. At this point. Okay. Now I obviously want to put this as some sort of number, which maybe if you go ahead and let's see. Actually, let me go ahead. I'll leave this for now. We'll worry about that needs later. We'll come back to it. Right. The last time we could just say, oh, it's the initial population, but may not be in this case. So let's be a little careful. Okay. I want to solve this for P. Right. So the next step might be, okay, well, maybe we can take M minus P to both sides, multiply it, bring things over, factor out, whatever. We can totally do this. What I'm going to do is I'm just going to take the equation here, and I'm just going to do the reciprocal, okay? This is still a true statement, right? Still the same thing. As long as I just flip the fraction, it's still the same answer, right? But now, and maybe I'll rewrite this right side as e to the minus c and e to the minus kt. This left side is going to simplify a little bit because I'm going to get m over p minus 1, right? Because p over p is 1. So that's helpful because it just leaves us with 1 p now. Okay, so that's kind of why I did that, just to save some time. Okay, now I want to solve for p, right? So what should my next step be in this case? Add the 1 over. Good. So when I add the 1 over, I'm going to get m over p equals e to the minus c, e to the minus kt plus 1. Okay. Again, there's a couple ways to do this. You can either flip this and then multiply the m, or you can just, what's going to happen is you multiply the p up and you divide this side over. But what we're going to be left with is p equals m over, and I'm going to put the 1 in front, 1 plus e to the minus c, e to the negative k. Okay, so this is p, right? We're not done. I really want to try to write this differently. I don't want to have e to the minus c. I want to see if I can put it in terms of something I'm familiar with. So that's exactly what I'm going to do here, okay? And the way we're going to do that is maybe, let's see. Let's come back to, well, actually, we can probably go here. That's okay. Okay, so I have this, right? Now my population is going to start at some initial point, correct? It's going to have some p naught. You're going to have some starting population still. It's going to work from. Okay, so when do I have that initial p? What time do I have that initial p at? Time 0, right? When t equals 0. Good. So if I want to simplify this e to the minus c part, given my PO, I'm going to take PO and t equals 0 and plug it into this equation. So I'm going to get PO equals M over 1 plus, now, when t is 0, we get e to the 0, which is what? 1. Okay. So I'm going to get just e to the minus c. Okay. Now I want to kind of get what this is supposed to be, which the book ends up labeling that as A. It calls it the value A, which I'll end up calling it A here as well. But let's try to solve for that e to the minus c first. Right. So what would be my first step in this case? To solve for e to the minus c. We're going to multiply that up, and then that PO can go ahead and divide as well. So I'm going to get 1 plus e to the minus c equals m over p naught. Okay. So what is e to the minus c? Equal to. Good. Minus 1. So this is absolutely fine. Or I can write this. Get a common denominator and get this. And we're going to call this value A. Okay. This is going to be the number that I put in front of that e to the negative kt. Okay. I'm going to call this A. So each time when you do this problem, you're going to have to calculate what that A is going to be. And then from there, we can just plug in and that's going to be our equation. Right. So in my case, right. So finally, to end all this off, maybe I'll do this in red now. If I have the equation dp over dt AP times 1 minus p over m, then p is going to be equal to m over 1 plus a e to the minus kt, where a equals m minus p initial over p initial. Okay, this is our solution, right? If I want to get this a value, I just do the subtraction and plug it in. And that's going to be it. Okay, so that's my solution. Okay, took a little bit, obviously. Yes.
On the right half of the board, the third line down. Sorry, the right.
Here? Okay.
Because for a second there, it looked like you had
And okay, yeah, it's minus. Right, which carried over from here, which is minus. I just yeah, not the best way. Over m minus. Okay, well that's what we ended with there. That's our equation. Okay. Great. So hopefully you kind of followed through. Ultimately, that equation over there is what we need to have. Okay, and so we can take that and we can use it for our equations. Okay. Yes.
So we have that final expression.
Is p supposed to be what?
So you know how we flip it over?
Uh-huh.
P over m minus p.
No, because it's only to the -1 if you flip one side, but you don't do the other side. We flipped both sides, did we not? We flipped both. We didn't just flip one. Okay. So yes. So that's why it's not. So I can do that with both sides. Yeah, when we flip both sides, the -1 doesn't matter. Okay. So we're looking at this. Okay. The book has another example that was based off of so what was his name? By a guy named G.F. Gauss, like a biologist, who was studying this kind of population growth. And it kind of wants you. The problem ends up having you kind of testing between both. There's not really many problems like, or ones I can do easily, like in front of everybody without having a calculator extensively. For this, at least for this idea, but what ended up happening is he had, had some points up here, and so initially you say, well, let's try the normal population growth model, and while it works for a bit, it gets off, but that it turns out that this logistic one really is the one we're looking for. It kind of fits the data really nicely, and so for all those tests there, this is the one we want to aim for, right? This is a lot more accurate and better than the ideal case would be, even though the ideal case still might exist, just not. That's good. Okay. Do we want to do a example real fast? Suppose so. Okay. So we're just gonna find. I'll just do like number 2, and then we'll call this section good at least. Okay, so number 2 in the book says we have a population that grows according to the given logistic equation, right? So we have some population that's going to grow according to given equation, dp over dt, which is going to be equal to 0.02p minus 0.0004p squared. Okay. And we are asked to find carrying capacity Okay. We are asked to write the solution. I think it gives us yes. So it gives an initial population as well, which I should write, which is P0 equals 40 in this case. And then C, what is after okay, so this is our problem. We're given dp over dt is 0.02p minus 0.04p squared with the initial. We want to find carrying capacity k. We're going to write the solution to the equation. We want to find what the population is after 10 weeks. Good. So right, if I want to find carrying capacity in k, I should probably put it in the normal form that these equations are supposed to be, right? Because right now it's not really in the form that it should be, right? So if I want to write it to look like this, right, what should I do? So we're going to get dp over dt 0.02p, which we're going to factor out. Then we're going to have 1 minus. This one, it shouldn't be. So whenever we factor out, right, we divide from whatever the number is. So I'm going to have 0.004004 divided by 0.02, which ends up being, it's going to be, I'll write it in decimal form, but actually it's 0.02 again. 0.202 squared is actually 0.004, funny enough. And this is times p, like that. But I definitely want to try to write this as p over m, right? So I need to try to figure this out. If I try to rewrite 0.02 as a fraction, which you might have to do occasionally, this is the same thing as 1/50, so it works out pretty nicely. So we're gonna get 0.02 p times 1 minus p over 50. Okay, so this is the same thing as that equation, right? But now it's in the form that we like, right? So what is the carrying capacity in that problem? It's, yeah, the carrying capacity in this case is 50, right? We're looking for m, which is the value down here. The value there is 0.02 is going to be my k, which is the other part I need, but those are different, right? So m is 15, k is 0.02. Okay, now, so that's part A. Part A is taken care of. Part B says to write the solution, right? Now for the solution, I needed k, and I'm going to need m, right, along with my PO, right, in order to write it down. So first, before we plug in my numbers, right, let's see what A is supposed to be. So A needs to be m minus P initial, P naught, P0 over P0. Okay, so what is m? 50. What is P naught? 40. That's my initial. Good. And then we divide this by what? 40. So 10 over 40. Okay, so that's how simple the A is. You just plug in the numbers and you get it. Right? Once we have that A, I take A, M, and K, plug it all in, and so we're going to be left with P equals 50. This 50 is M over 1 plus 1/4 e to the negative 0.02 t. Okay. Can we simplify this a little bit? Maybe, right? If I didn't like this 1/4 here, I could just take 4 and multiply the top and bottom, kind of cancel it out, but otherwise this is 1. Okay, that's all there is to that. Okay, is that making sense there? Is that good? Again, if you feel worried, it might be the work that we did, but the work we did was just to be able to use this, and this is all you're going to be doing. Okay, you're not going to be solving equations, though it would be good to develop that skill. Right? I'm not saying to not do that, but understand it takes a bit of time. So this is my equation. Okay. So the last part is define what population is after 10 weeks. T is in weeks, by the way, the time that we're working with. So if my time is in terms of weeks already, and I want to find what the population is after 10 weeks, where do I put that 10? Into the T. Good. So we get P equals 50 over 1 plus 1/4 e to the negative 0.02, which you can feel free to calculate out. This is going to give you some number, but that would be okay. Okay. You might encounter some problems where it might ask you to find a population, like say if I have this population, what time, how long does it take? Right? That just means that I plug in for P and I solve for T, which is a bit of a task, but nothing you can't do. Obviously, I don't know if I can do that on tests just because these problems are so complicated as they are with the numbers we want to calculator. Other than that, that's really just the main gist of the section. In these sections, you're going to have ones that you really want to think about and kind of understand. See, you can take these different situations and kind of apply some of the thinking to it, but this is the big idea. In general, right, we have this equation where we can solve this logistic, and in general, there's I keep saying that we can really modify this in a lot of ways to give us particular situations in order to really model any sort of population. So this is really powerful. It's powerful that we can solve all these and do something with them. It's very useful. Okay. Any questions on this? This is 9.4, so that's good there. We're still doing 9.6 though, so don't leave it. We're gonna do 9.6 with that, which is, so I'll leave that up for now. Let me erase this. Okay. So what I would consider this section to be is just a really brief sort of introduction to this idea of systems of differential equations. We're just looking at a brief application of it. We really can't solve them at the moment. When you take differential equations, you're going to be doing a lot of these. They're going to be fairly simple. But for now, we'll at least kind of see what we can do. But this is one of the first topics you talked about there as well, where we cover these predator-prey systems. Okay, so so again, we have predator prey, right? So going off this idea of modeling, I want to model what happens in nature, right? Now, the population we've been doing so far has just been kind of independent of itself. We didn't worry about any sort of like, it was just how's the population going, their own resources. We were worrying about, oh, does the presence of this animal affect the growth of this animal? Does, in this case, we have predator prey, right? Does this predator needs a certain amount of prey to survive. And if that prey isn't very available, then the predator isn't going to live very long. Same thing if there isn't any predators to stop the prey from growing, the prey is going to grow exponentially, right? So we're going to build this system here. We're going to kind of talk through it. And we're going to start off by kind of setting up each situation, okay? So we're going to start first with prey. So let's say the system of prey, right? So we're going to assume at the start that in an ecosystem, the prey has no predator, right, to attack, right? So that means that it can grow as freely as it wants. It can keep growing. It's not going to stop. It's just going to grow exponentially, okay? In this case, we can just kind of model this system, and they use RW, so I'll use the same. So I'm going to use R to represent the prey, dr over dt, and this is going to be equal to K times R. Again, K, very similar thing. They're going to grow this relative rate, like K is a positive number, it's going to increase, right? Now, so that's our prey for now, right? Now let's we'll leave that situation. That's the prey, what the prey would be if there's no predator, okay? Let's kind of think about what the situation would be if I have predators, but I don't have any prey, right? In that system, things aren't going to work out very well, because what's going to happen is they're just going to die off, because that prey is what they consume. It's what they eat to live, right? So if there's none of that, all we see is decrease, right? So this ideal system, right? Again, ideal in quotations, really just in the presence of no prey. So I'll call it a W. Is going to be, instead of positive KR, I'm going to have negative R times W. Okay, now this little r serves the same purpose as K. We just don't want to use the same rate, right? Because they're not going to change at the same rate, right? They might vary depending, right? But this is my prey system with no predators, and this is my predator system with no prey, right? But we know the reality of the situation is that, they both are present, right? They're both interacting with each other, right? And that interaction is going to ultimately affect what happens in these equations, right? So I'm not just going to leave this here, right? They're going to interact with each other, right? And this interaction, we're going to represent by taking the two numbers and multiplying, right? If there's more of one, there's going to be more interactions, right? If there's a few predators but a lot of prey, there's going to be a lot of interactions between them. So on both of these equations, I'm going to add an R times W term. Okay. Now, in the prey situation, right? It was all happy it could grow with the predator there, but as soon as the predators start appearing, they're gonna start decreasing, right? Because now the predators are eating them. So to represent that change, we're gonna have minus A times RW, right? So R again is the prey, W is our predator. As they interact with each other, there's some constant dependent upon, but they're going to decrease as those interactions increase, right? Good. So this is a good model for the prey system, right? This is how prey and predator interact with each other. And then K, A, R, and then what we're going to see, B are going to vary depending on the situation. In this case, the predator is happy that there's prey around because now it can actually start growing. So instead of minus, I'm going to have plus B times RW. So from this is a very effective model of a predator-prey system, right? We can kind of see what's happening in each case. We see without predator, it increases, but it starts decreasing once they appear. And without prey, this decreases, but starts increasing after they appear, right? So again, this differential equation stuff is really powerful to help us to connect these together to see how the rates are going to change. And so what we're going to want to do from this point, actually, so I'll give the names for these real fast. These are called the predator-prey equations. Or the name of the book is for these, if you were doing the problems and you come across this, is called okay. This is what this system is called. Okay. What these equations are called. Now, let me address again. This is different from what we're used to, right? Because normally I would have in this equation maybe just an R and a T, and then in this equation I would just have like a W and a T. But now W's in the R equation up here, and R is in the W equation here, right? And this is, as it says, as it kind of implies, this is a system of differential equations. So we have two rates that are fighting against each other, essentially kind of working with each other to make one whole system. Okay. So good. So let's take our example here, and we're just going to kind of work through this. We're going to kind of think through this and see what's going to happen. I'll take the example in the book just so I have the numbers for sure, so we don't have to calculate too much. But let's work. Okay. Good. Any questions on this front so far? Kind of makes sense how I set that up. Hopefully, how they interact with each other. Obviously, if R or W increase, the interaction is great. Okay. So I'll frame this in a little bit different than the book does, but so let's kind of take an example of this. So I'm gonna have K equals. So we're gonna get some numbers. 0.08. We're going to have A equals 0.001. B equals R is 0.02, and B is equal to, I think it's 0.0000. Yeah, 40. Okay. So this is the system we're given, right? Again, we're gonna take those and plug those into the equations. So let me go ahead and do that real fast. We're gonna have dr over dt equals, okay, 0.08 r minus 0.001 rw, and we're gonna have dw over dt equals rw, which is negative rw, sorry, negative 0.02 w plus 0.0002 rw. Okay. So when we got in a system like this, right, and we want to study it a little bit, the first question that might arise in our mind, right, we've been doing these problems, this one's a bit complicated. We kind of work with equilibrium solutions, right? We want to find those constant points, those points where we're going to have a zero rate, where it's going to kind of like slope off. Okay, so let's talk about that. Equilibrium solutions. If I want to find equilibrium solutions to these systems, right? I need my slope to be zero, right? But I don't just want one slope to be zero. I need both of them to be zero, right? So to solve this particular system, right, or to find the equilibrium solutions, I would want to take. We're going to have 0.08 r minus 0.001 rw. That equals 0, and we're going to take 0.02 w plus 0.0002 rw, and set that equal to 0. Okay, because when both of the slopes are 0, those are going to be my true equilibrium points. Those are going to be the nice points, right, where they both kind of are in perfect balance with each other in a way. Okay, so at this point, I have two equations and I have two unknowns. Okay, let me try to rewrite some of my variables here so we can see it clearer. My arms just not very good. Okay. Can I take these two equations and solve them for R and W? What do we think? Is there an easy way for me to do that? Well, we wouldn't want to set them equal to each other, really. I mean, you could, but I don't know if that would be the best solution. That might just make it more complicated. Any other suggestions? Right. So we can factor an R out the top, and we can even factor a W at the bottom as well, right? So I'm going to get R times 0.08 minus 0.001 W equals 0. And on the bottom, we're going to get W times negative 0.02 plus 0.00002 R equals 0. Okay, good. So these are both, this is equal to 0, right? Let's just take the first equation at this point, right? Since these are both equal to 0, right? Or sorry, the whole thing's equal to 0. Either one of them being 0 is going to solve this system. Okay? So R is 0 solves this, right? So I can let R be 0. Okay. So this R being 0 will solve the top equation. So now let's plug it into this bottom equation and see what W is supposed to be. If I take R and put it into this equation, what's gonna happen to this term? This 0.0000. It disappears. So I'm left with negative 0.02 W equals 0 So what does that leave W to be? 0. So W has to be 0. Okay. So this is 1 there. Okay. Again, R is 0 is the solution to this guy, right? And whenever I plugged in 0 here, I got negative 0.02. And inside was negative 0.02 times W equals 0. The only solution to that means W is 0 itself. Okay, so they both have to be 0. Okay, but that's not the only option, right? We have another option because I could have this part be equal to 0. Correct? Right, so R could be 0 or this part could be equal to 0. And when I set this part equal to 0, I'm going to get, let me go right off the side for the moment. We're going to get 0.08 minus 0.001 W equal to 0, which there's some decimals, we could solve this, right? We're going to get W equals, in this case, it's going to end up being 80. Nice, we equal to 80. Good. Okay. Now, if I take this 80 and I plug it in up here, plug it into the second equation again, I get 80 times this thing equals 0, right? But in that case, that 80 doesn't matter, right? Because obviously for this thing to be 0, the inside has to be 0. So again, I could take the negative 0.02 plus 0.00002R. Sorry, wait, no, that's right. And set that equal to 0. Right? So if that's the case, right, we could solve this again, and we're going to get R equals 1,000. So in the end, I have R equals 0 and W equals 0 as a solution, or we have R equals 1,000 and W equals 80 as those. Okay, but these are going to be the 2 points where my equation is in equilibrium. Okay, where my the predator and prey kind of balance each other out perfectly. Like it's kind of a stopping point before one starts increasing, going into the other starts decreasing. So 0, 0 kind of makes sense, or 1,080. Okay. Please, if you have questions on this, please ask me. Really, this was just solving equations. Obviously, there's some more complicated numbers, but that's all there is, right? For the most part, you should be familiar with this. Maybe the biggest new thing is if I want to find equilibrium solutions, I have to set both of them equal to 0 because I have to worry about R and W. Okay, questions for me? Anything? Good. So those are my equilibrium solutions. Great. Cool. That helps. Why not? So the next thing is you know what I guess what do these graphs look like? Can I figure out what the solution to the system looks like in some way? Can I kind of see it? Can I do a direction field to find it? And we absolutely can. Okay. What we're going to do is, and I won't go too much detail on like how to get in all the values and stuff because it might take a while. But the next thing we might want to do, right, is we might want to, be able to see, instead of worrying about this time for the moment, let's kind of see how R and W are related to each other, right? And so what the book does is it says, can we find dr over dw? Or wait, dw over dr, like that. I don't think it matters too much, but so instead of doing dr over dt and dw over dt and seeing how both are related to time, I want to see how they're related to each other, right? Because that's going to help me to make a plot for immediately, right? Instead of having a third variable, I just have my two variables, right? To find so if I have dw over dt, and dr over dt. All right, which this is going to be negative 0.02 W plus 0.00002 W, and this is equal to 0.08 R minus 0.001 RW. Like that. Okay. Is there a way that I could take these and find what dW over dr is supposed to be? Yeah. Just divide the two, right? Because dW over dt over dr over dt, the dt's are just going to cancel out, right? So if you want to find the rate between the two, just divide the two. So I'm going to get dW over dr equals negative 0.02 W plus 0.00002 RW over 0.08 R minus 0.001 R W, just like that. Okay, great. So this is my differential equation relating W to R, right? So this allows me to kind of create a graph, which it takes a little bit to plug in all, the different values. But what we're going to end up having is something that looks along the lines of my slope field is going to look something like this, right? And so if I were to take a particular solution and graph it, right? For example, it might give you an initial value somewhere, maybe down here. Then you would want the path that connects all those together, which in this case is going to be like a little egg of sorts. Okay, so again, direction field and just kind of connecting all the slopes together is going to give us something like this, right? Where, let's see, this is the r-axis, and this is the w-axis. Okay, so again, you might just be like, well, let's see what's going on at this point. Well, let's think through this, right? So this equation should give me a graph that looks like that, right? Whenever I kind of plot it, or the solution looks like that, like kind of a circle. So let's think through it. Whenever so there's going to be a certain point, right, where if we start here, for example, my circle, right, as my predator population might be a bit low, right, but as my prey population starts increasing again, there's going to be slightly more and more predators, right, until a certain point where we hit the apex, right, and the predators start outnumbering the prey, and so then we start going back down the prey direction, but the predators are doing pretty well. But oh no, we're low on prey again. So now we have to start going down, right? So the predator population starts going down, but because the predator population's down, our prey population starts increasing again, right? So the picture makes sense. It makes sense of what we would imagine is happening. So our system kind of works perfectly together. It kind of all holds together, which is very nice. And so if we want to, so that's the idea, right? We can see that the prey population is going to increase, but then as soon as the predator population comes and matches it, it's going to decrease again. But then as soon as the prey population decreases too much, the predator population is going to decrease as well. So what we can learn from this graph and doing all this equilibrium work, right, kind of finding our general solutions, is that the graphs for these things are going to look something along the lines of, so let's say this is R of t, and this is going to be W. Right, so again, let's say that the prey is increasing, right? What's going to happen is it's going to increase to a point where the predator is going to overtake it, so it's going to come down, right? And then similarly, right, the prey amount's a little low for the predators at first, right? But then they're going to come back And then as the prey are gonna start decreasing, but the predators are still gonna be doing a little well at the beginning, as they're still decreasing. But as soon as it gets low enough, they're gonna decrease as well, right? So what we have. Yeah, so you can imagine one kind of being like sine and one kind of being like cosine, essentially. They kind of flip off of each other, right? This one starts here and this one's slightly offset. Maybe I didn't draw perfectly, but that's the picture we should be getting here, which is that. So I'm gonna just stop it. Okay, we get this. They're kind of offsetting each other, right? So through all of this process, we could really take all of our information, put it together, and get to interesting results. Okay, so all that being said, I think it's just an interesting study to look at. Just a brief overview of that, which obviously we can get to the. Again, there's only 3 questions, and I think the deepest question asked on homework is just to find the equilibrium solution potentially, and then I might ask you to find if it's determine if it's predator-prey or competitive or cooperative, which let me address that last before we leave. It's gonna be the last thing. Okay. So you're going to see these two. We only covered the predator-prey one in detail, but we have 2 other types, which is cooperative and competitive, that can occur right in nature within these 2 systems, right? The predator-prey one, what we saw is we have. So I might use the same variables for each one, but obviously the variables will change depending. What's going to happen is whatever the sign is on the front terms, it doesn't matter, but the terms here need to be opposite of each other, right? Which is what happened here, right? The RW in this case, what would happen is obviously as there are more prey, the predators increased, but also the prey decreased, right? So they do the opposite of each other. They're going to kind of exchange, okay? And so that's what a predator-prey system is. If I talk about competitive systems, these are ones that are just bringing each other down in every aspect, right? So they should both be minus. Okay, so if you get to a system, they're both minus on this end, that's a competitive system. Okay, one of them's trying to win out ultimately in the end, so there's subtraction of both. As you might expect, the cooperative system does the opposite of that, where it helps in each case. So I might have RW, but they're both going to be. Okay, so again, the sign here doesn't matter as much. Mostly it's what happens over here, right? So these need to be opposite signs. So it could be plus minus or it could be minus plus. That's why I have it flipped. Here they both need to be minus and here they both need to be plus. So that's how you tell the difference between a cooperative system, competitive system, and predator-prey system. Okay, cool. Yes.
So how much this would be on the test? Like,
it would be one question. I think I would just ask it'd be like easy numbers. It'd be like a equilibrium solution, and I might just have you say which one it is, and then it's like equilibrium. Okay, I can't ask much from it, so that would be it. Okay, cool. Well, that finishes chapter 9 for us today. We're done with chapter 9. Fantastic. We went through 4 chapters. Jeez. So we're gonna do chapter 10. The next 2 days, we're gonna finish chapter 10. And then next week we start chapter 11. Which is my chapter. You too. Thank you so much.